Hopefully everyone can see the slides, and I will pass it off to Jacob to give a little introduction.
Thanks for saying that, John. So hello everyone. Thank you very much for joining us here today. As John mentioned, we are recording this session, so if anyone joins us in late or if you want to see this presentation later, you will be free to do so. We'll publish this later. Today it's going to be my name is Jacob, and I'm joined with my colleague John here. We're both applications engineers at Safety Power. Our presentation here today is going to be on it's going to focus on ultrafine particles and using DPF technology to treat them. So just a bit of logistics first for you. So we'll ask that everyone mute themselves. It looks like you've already done that, so thank you. If you have questions, please post them in the chat in the meantime, and then we'll take all your questions at the end of the presentation, just to keep the flow of the webinar going. We're going to split up the presentation a little bit between John and myself, so we'll take you through the agenda here real quick. John will start off. He's going to give you a bit of an introduction, basically, what particulate matter is, what it consists of, the health impacts, and then really define what ultrafine particles are and why they are important, why we're talking about them today. And then he'll just go through some of the basic things about how DPF filters work and how they mitigate UFPs or ultrafine particles. I'll then take over and kind of put it into a bit of context. We'll go through some of the history of DPF in automotive. We'll then compare it to what has been done and is currently being done in the off-road industry, and then we'll finish off by talking about some upcoming regulations and changes as we see it today. So that said, as mandatory with all our webinars, just a quick introduction as to who we are and what we do. Safety Power Inc. is a manufacturer of emission control systems for large gas and diesel generators. We have over 600 installations to date, well over that at this point. And we work with all the major engine manufacturers, so experience all across the board. Our signature product is really the EcoCube product, which is a sort of highly compact integrated system, which integrates an SCR system along with a DPF and acoustical mitigation and oxidation catalyst when needed. This is a product which we really spearheaded and has been on the market for 10 years now. And again, this presentation here, we're really going to focus on ultrafine particles and why they are important. And so with that said, I will give it to John, who's going to give you the background.
All right, thank you, Jacob. So when we say particulate matter, it's actually an interesting thing that particulate matter is actually a complex mixture of substances. So it's composed of both volatile and non-volatile species. So on the volatile side, you've got acids and hydrates and all kinds of liquids. And then on the non-volatile, it's actually primarily carbon. So that's what's causing that black plume when you see any kind of truck accelerate on the highway. You see that black smoke coming out of the exhaust. That's the carbon. But there's also oxides and metals. And so these non-volatiles generally kind of agglomerate into these larger, more coarse particles that you can see in this bottom microscope image. You'd imagine this is what you'd see if you could capture the PM and look at it. There'd be a few of these large particles, but there'd also be an innumerable amount of these very small nanoparticles or ultrafine particles. And what we mean by ultra fine is really anything that is smaller than 100 nanometers in diameter. So you can see here on this plot, there are quite a number of particles below 100 nanometers. And looking a little bit closer at this plot, we also notice that if you consider the mass of all the particles you're able to capture from the exhaust, most of the mass is actually in those larger particles. So about 90% of the mass is accumulated in a very small number of particles, but those particles are very large. So what you have is a large number of small particles that don't contribute very much to the mass. So when you say I'm reducing PM, it doesn't necessarily mean that you're reducing the ultrafine particles. And that's a very important point. And just to sort of illustrate that, it's sort of like if you're making yourself a sandwich and you drop the sandwich on the floor, and if you're very hungry, you might think to dust off that sandwich and probably remove any kind of large visible particles from that sandwich before eating it. But the problem with that is what you don't see and what you're not really able to remove are the thousands and thousands of microscopic viruses and bacterium that might be on that sandwich as well. And those are actually more harmful to you. So even though you remove the dust or the big dirt on the sandwich, those small particles are very harmful. And we'll also see that ultrafine particles act in a similar way, and that they're also potentially even more harmful to you than the large, coarse particles in the exhaust. And the reason for that is small particles have a greater tendency to penetrate deeper into your lung tissue. They can even go as far as your bloodstream and have definitely been linked to all kinds of premature deaths, heart disease, lung disease, etc. So considering small particles is definitely something important if you're concerned with the health effect anyone in and around generators that might be running. The ways that we're able to measure PM in the field are basically, they fall into two categories. So the first one being gravimetric, which means by mass. So what you're pretty much doing here is you're allowing the exhaust to flow over a filter. So method 5, it pretty much just captures the PM on a filter that was weighed, and then the PM would accumulate, and then the filter is weighed again, and you get a difference in mass. And so you end up reporting something in grams or in pounds per hour. And the other method here, 1065, is similar, but there's actually some air that comes in and dilutes the exhaust as well. But in the end, you still report mass, so grams or pounds. However, in the European Union, they also focus on particle number as well. So this is interesting because now they're able to capture all those very small particles, which we said don't really contribute to the total mass, but there's quite a large number of them. So using these particle number counting devices, they're able to measure any particles greater than 23 nanometers, which would find that ultrafine particle range. So now I'm going to quickly get into what a DPF is, or diesel particulate filter, and why they're important for considering for PM. So safety power, as Jacob mentioned, our EcoCube product comes or is able to come with DPFs. And what this is basically a filter. So you can imagine the exhaust flow comes in from the left. Any kind of solid particulates or even liquid particulates are filtered and they're captured on the surface, or will sometimes penetrate a little bit into the filter. And then over time, the particles will build up and form this sort of thicker layer on the surface, which we actually call the cake layer. So as this cake layer gets thicker and thicker, you can imagine the back pressure on the engine will increase more and more. And so there's actually a balance point for these passive DPF filters where the cake layer grows to the point that the pressure increases. But what happens is when you increase the exhaust temperature, a process called regeneration occurs, and the cake layer is reduced. So the thickness goes down again through a process of oxidation. So really, this is a way that we can tune and balance the pressure drop while also maintaining this cake layer. And looking a little bit closer at the filter and at the cake layer, we notice that, first of all, like I said, the process is controlled. So in a passive DPF system, as opposed to an active one, the cake layer is maintained. And this is actually important because the cake layer is the primary filtration method for very small or ultrafine particles. So without the cake layer, the UFP retention is not as great. It's actually interesting that the particles are acting as a filter for themselves. And if you look at a green DPF, so one that hasn't seen PM yet, it actually starts to accumulate this cake layer, and the filtration efficiency goes up very quickly. So typically during a commissioning process, after 8 hours of burning and testing the entire system, this cake layer will have formed, and the filtration efficiency can exceed 90%. And then right here, we notice that throughout that range, so for all particle sizes, a passive DPF system is very efficient at removing the PM. And of course, it's more efficient at removing. It's still a filter, and filters are just generally better at doing that. But even in the nanoparticle range, it's able to remove 85 to 90% of the ultrafine particles as well. And that's just illustrated here on the graph on the right, where 2 orders of magnitude of difference between non-DPF and a system with a DPF in terms of particle number. So you're able to capture and remove a lot more particles with a DPF. So with that, I will pass it off to Jacob, and he'll talk a little bit more about the history of DPF.
Thanks, John. So before jumping into that, just to quickly summarize that first half there. So ultrafine particles, UFPs, are particles that are below 100 nanometers in size, right? The majority of the mass in particulate matter consists of the larger particles. However, the majority of the particle number is actually in those smaller ultrafine particles. And as John pointed out, the sort of main point that we're making here is if you're just looking at the gravimetric side of things, i.e. you're just focusing on the mass reduction of particulate matter, you're not really considering the ultrafine particles, which, you know, of course, PM in general is harmful, but ultrafine particles, as we pointed out, are also harmful. So that is important to look at, and that's sort of the main point we're making there. Now, that said, let's sort of put that into context. Let's talk a little bit about history. So DPFs are nothing new. They've been you know, around for a long time, especially in the automotive market. They have a long history. One of the first DPFs developed for passenger vehicles was in the 1980s for the Mercedes-Benz 300 ST and 300D. So that's the vehicle there, and sort of a DPF. This was known as the Mercedes turbo diesel at the time, and you know, it was a relatively simple kind of DPF, but that technology has since rapidly advanced, especially in the 15 to 20 years that preceded that first implementation. And it wasn't really until the early 2000s where DPFs became very widespread, especially in the heavy-duty trucking industry, where these days they're pretty much, as we'll point out, they're pretty much everywhere. So in the meantime, there was a lot of progress made, with just improving the engine technology to lower emissions, as I'm sure you all know, and there were phenomenal advances made in that respect. So I'm sure the people on this call probably are even more familiar with these than I am, but just quickly going through some of these methods. One of the things used, for example, was injection pressure. So it was found that at higher injection pressures, we would get lower PM emissions in the exhaust. So that could be seen in the top right graph there. Of course, like anything else, there are diminishing returns. So the higher pressure you use, the less benefit you get. So there's an optimal point there, like anything else. Another example is injection timing, and I could direct your attention to the bottom right graph there. I'm just going to move this out of the way. And so it was found that if you inject fuel earlier, you also get less PM. And you could see, it's quite a good reduction. You could get as much as 40% in some cases. But the trade-off there is you get higher NOx emissions, which of course you don't want. So again, there's an optimal point there. I'm sure many of you have seen that graph where you sort of optimize the NOx versus PM, and the less PM you get, the more NOx you get. So that's this sort of scenario. And there's been many other advances to lower emissions within the in-cylinder, including the combustion chamber itself, turbos, and direct injection. So especially if you compare it to engines, from the 1980s and then before that, it's really day and night what's being exhausted from these engines. Now they've made great strides. That said, there's really, even so, you will still always get better performance with a DPF, and so that's what we're showing here. So if you look at this graph, basically what we're looking at here is particle concentration on the y-axis here over cubic centimeters, and then the x-axis is really particle diameter, but that's not really the important part. Basically, if you look up here, this is generally the sort of concentration you get in the exhaust for PM out of an engine without a DPF. So we're looking at somewhere between 10 to the power 6 to 10 to the power 7 particle concentration per centimeters cubed, versus with a filter, a DPF filter, you're looking at around 10 to the power 3. So that's about a 2.5 order of magnitude difference, which is obviously very substantial. In fact, if you look at where the DPF, and this is a bit of extra information, but if you look at this region here, of course it depends where you are and which region, but the DPF system essentially brings you down to what could be considered ambient levels in many ways. So really a significant amount of PM reduction there. So just talking more going back to regulations and the automotive industry, really, because the automotive industry does lead the way in terms of emission requirements for various reasons. But so here's some of the current regulations in place for light duty vehicles. We've got EPA Tier 2, which basically requires all vehicles to use DPF. And in Euro they have something very similar, the 5A-B. Basically the same as above. Any vehicle would require a DPF to operate in these days. For heavy duty vehicles, similar story. In North America, EPA is really what set the standard. The requirement for the on-road is 0.01 grams per horsepower, which, if you're not familiar, that's basically half what it is from the off-road industry, 0.02, right? So basically forcing all the engines to use DPF, right? So no ifs or buts, and same thing in Euro, just in grams per kilowatt hour. It's worth noting as well that in Europe, what's interesting, and John kind of touched on this a little bit, they don't just rely on gravimetric methods, right? They also take into account the particle number, and in those instances, there's really, again, it does come down to the same thing, but you simply cannot meet those requirements, especially the particle number requirement, without a DPF. And in some ways, that's basically an admission by manufacturers that the most effective way to truly reduce PM, especially ultrafine particles, it is with the use of a DPF. So now, taking that and sort of comparing it to the off-road industry. So for various reasons, the off-road industry is not quite as stringent as the on-road. As most of you probably know, the sort of gold standard in the off-road industry is Tier 4 final. That is the most stringent emission levels that we have for diesel engines. That said, interestingly, many engines are able to meet at least the PM part of the emissions using in-cylinder technology alone. So they would just have an SCR system to reduce the NOx, but not necessarily a DPF to reduce the particle number, which is great. But as we sort of pointed out, that would do very little in terms of reducing the particle number. It's basically focused almost entirely on reducing the particle mass, which basically just mitigates the large particles. And so because of this, this is starting to, regulators are starting to catch wind of these sort of things, especially those in California. And so they're trying to go slowly above and beyond the EPA in the hopes of sort of breaching this gap between on-road and off-road. And CARB especially is one of the ones leading the way in these sort of things. So there's a study that was done by CARB. It's not published yet, so we're just talking about it because we were given a draft. But briefly, I'm just going to take you through some of the main findings in that study. So basically what they did is they compared a Tier 4F certified engine, which just has an SCR, and then compared it to one with an SCR and a DPF. And again, I'm not going into a lot of detail here, but just mainly the results, they essentially confirm what we already know and we're already suggesting, and that's that DPF provides a significant advantage, and it does so across the entire D2 cycle. So the results were that for PM emissions, speaking for mass specifically, there's about an order of magnitude of improvement there when a DPF is used versus when it is not, even though it's meeting the Tier 4F requirements. And for particle number, and this will be a trend, you will see the impact is even larger. There's a 2.5 order of magnitude improvement there when a DPF is used. So it's very substantial, obviously. Now, we all know that emission control systems are they're a rather expensive piece of equipment. No manufacturer is going to go out of their way to install this equipment, and especially make it standard in their equipment, unless they're required to by the regulators, which is a sensible thing. We live in a capitalist society. If one manufacturer does and the other does not, they will not be competitive. This is a sensible thing. That being said, what we're sort of pointing out here is that when you're looking at best available control technology, it really does need to include DPF. So here's just a few bullets here. DPFs are installed on millions of vehicles every single year. It is a technology that is widely available. They are subject to harsh environmental conditions and vibrations on the on-road in the on-road industry, much harsher than anything that they would see in the off-road. So this is a technology that is available, is proven, and is robust. And Safety Power leverages this, existing technology and highly tested technology. I don't know if you know this, but the DPFs that we use in our systems, for example, they're actually the exact same DPF canisters that are used in the on-road trucking industry. So we're just basically taking that technology and applying it to off-road, leveraging the experience there, and also makes it very easy to clean when required because the infrastructure already exists. So DPF realistically represents what is the best available control technology. And so now what we'd like to do is sort of just put this in the context of an example for you. So one of our engineers, they went through the EPA database, and so they pulled out some of these numbers here. So we're going to use them in a case study in the next slide here. But basically, on the top here, you could see the average PM output from a Tier 4 certified engine, which does not have a DPF. And down here, so what we're actually going to do is compare it to a Class A truck, right? So what we're doing is we're comparing off-road to on-road here. And so for a typical Class A truck, which again, all have DPFs, this would be the typical PM output. And so that's about a 23 times difference in PM emissions off the bat. And then taking some info from a CARB study in terms of PN, again, the difference is much more substantial. It's around 445 times the difference between certified engine and a Class A truck with a DPF. Interestingly, when it comes to smaller generators, sometimes it's literally the exact same engine that's used on a truck that is also used on a generator, especially if it's smaller than 350 kilowatts or so. And the funny thing is in that context, if you take that same engine on the road, it must have a DPF. But if you take it off the road and you attach a generator to it, all of a sudden it typically does not require a DPF. And I think that's sort of where these issues are coming from, and why regulators are starting to look at this increasingly. And a lot of it you'll see is, I think, because and this is my opinion anyway, the regulations for the off-road industry are a little bit more relaxed, simply because it was always kind of expected that there would not be so many of these generators, and that they would not be running quite so much. So anyway, let's go through this case study, and then you'll see you'll see why that comes into play here. So here what we're doing is we're taking a typical 3 meg Tier 4 certified generator, and we're comparing it to what it would be equivalent to in terms of Class A trucks. So off the top, looking at power output, 1 3 meg engine works out to about 11 typical Class A trucks. And we've got all the calcs down here as well if you want to see them. Then in terms of PM emissions, that's 246 trucks. So starting to get pretty substantial there. And then for PN emissions, really very substantial. 1 3 meg generator is equivalent to about 4,700 trucks. And so if we take that example and we take it further and we apply it to a whole data center, right? Because that's really just one generator. As I'm sure you all know, these data centers, there's starting to be more and more of them. That there could be, hundreds and thousands of these generators put out. So let's just take as an example, just depending on the data center, there could be different number of engines and configurations. But as an example, let's take just a nice round number, 30 engines. That's relatively typical for a building, maybe with 2 phases. So if we apply what we had in the previous slide, and we basically multiplied by 30, in terms of PM emissions, for a data center we're looking at about, just over 7,000 trucks. And for PN, we're looking at over 140,000, right, for a single data center site. So, and that sort of hopefully paints the picture a little bit. It's like kind of when you're looking at risk, you have to consider both probability, but also severity. In this case, the probability essentially is low because that's essentially engines will not be running very often. So probability is low. However, there's a very large amount of engines outputting a very large amount of particulate matter, especially particle numbers. And so the severity is quite high. So the risk is there. And, if you were to think about it, especially when they are running during those odd hours, think of the employees that are actually on this site and being exposed to this amount of emissions, even during a short period of time. That could be something, at least for that employee, that is certainly concerning. And so if if those generators had a DPF, we would be seeing, it's still a lot of trucks, to be fair, but drastically less. Basically 380 trucks is the equivalent of a data center with 33 meg engines, and it's the same for both PN, we're saying, and PM, because the DPF would reduce both essentially. And so that said, let's just talk a little bit about some of the upcoming changes, at least as we know them today. So again, CARB is really one of the key drivers here. And so for the on-road industry, there are some changes scheduled. So for 2024 and onwards, PM should be limited to 0.05 grams per brake horsepower. So half of what it is today. And they're also bringing NOx down to 0.05. Again, that's in 2024. And then in 2027, further down even to 0.02. So very, very, very stringent emission requirements for both PM and NOx, already above the stringent levels that they are at now. And so there's basically rumors of Tier 5 upcoming as well. I believe CARB is pushing for that. And again, the rationale for this, I think, primarily is that really best available control technology should have a DPF, and many Tier 4F systems in the off-road industry do not have DPFs. So for Tier 5 levels for 2028 onwards, we're looking at basically a 50% reduction from what they are at today at the Tier 4 levels, which essentially, I believe, would make it a requirement to have a DPF. I don't think you would be able to rely on in-cylinder technology alone to achieve those PM levels. Now the good news is, at least for us and for people who use our systems, and a safety power EcoQ system with an SCR and DPF would already comply with these levels. For both PM and NOx, and also even for the lower NOx, the future value that's 50% lower. Essentially, intrinsically, the way our technology works is there is some safety factor in the catalyst, and if you were to inject just a little bit more urea, you would be able to get down to these levels. So essentially, making our systems future-proof, at least to the Tier 5 levels. And increasingly, it seems that air permits may begin requiring not just PM emission requirements, but also UFP reductions, and because of all the reasons that we've stated here. So really, guys, that's it. I'll give you a quick summary. Particulate matter is, an extremely complex substance. It consists of not just different compounds, but also different sizes. Ultrafine particles, which were the focus of this presentation, are particles which are below 100 nanometers in size, while larger particles consist of the majority of the mass, ultrafine particles consist of the majority of the particle number. And they have their own important health effects, which need to be considered. And so focusing on the mass of PM alone does not address the full story. In order to reduce ultrafine particles truly, it has to go through a DPF. And so it seems like the on-road industry is basically already there. And it seems likely that the off-road industry will be going in that direction as well.